The 47 heavy transports involved in delivering large bridge components required precise coordination and specialized vehicles for efficient assembly. The delivery to the upper ramp involved transporting massive components using specialized trucks. These trucks maneuvered carefully to position the parts precisely. This stage required planning to ensure that the heavy loads were delivered safely and aligned correctly for subsequent assembly, facilitating a smooth construction process for the upper ramp of the bridge. The assembly of the upper ramp involved aligning and securing large prefabricated segments using cranes and hydraulic presses. Workers carefully bolted the sections together, ensuring structural integrity. This phase was critical for providing a stable foundation for the rest of the bridge construction. The assembly of the lower ramp involved positioning and fastening heavy prefabricated segments onto the foundation. Cranes lifted the sections into place, where workers used hydraulic presses and bolts to secure them. This step required precise alignment to ensure stability and proper integration with the upper ramp, forming a continuous, robust structure. The new rounding element was a crucial addition designed to enhance the bridge's curvature, allowing it to follow the motorway's S-curve with a 1,000-meter radius. Fabricated with precision, this component was engineered to integrate seamlessly with the existing structure. Its installation involved aligning the rounded segments with the rest of the bridge, ensuring smooth transitions and maintaining structural integrity, ultimately contributing to the bridge's ability to handle complex turns safely and efficiently. The second night of construction commenced with crews assembling additional bridge segments, focusing on completing the remaining 100 meters efficiently. Bridge portals were delivered using specialized trucks, precisely timed to ensure seamless integration into the ongoing assembly process. Hanging intermediate elements involved using cranes to lift and position these segments between the gantries. Workers then secured them with bolts and hydraulic presses, ensuring precise alignment and stability for the bridge structure. Technicians connected data lines to synchronize the bridge's control systems, ensuring coordinated movement and communication between the modular segments. The project included 18 bridge portals, each a critical support structure. These portals were precisely positioned and secured to ensure the overall stability and load-bearing capacity of the bridge. Positioning involved carefully aligning each bridge component using cranes and hydraulic systems to ensure accurate placement and structural integrity. Connecting the bridge halves was a process crucial for completing the structure. First, workers aligned and secured the halves using hydraulic presses and heavy bolts. Precision was key to ensure the sections fit seamlessly, maintaining structural integrity. Once secured, technicians connected power and data lines between the halves, enabling integrated operation. This step facilitated communication for synchronized movement and control across the entire span. The bridge's modular design allowed for efficient assembly, reducing downtime. After connections were verified, final adjustments were made to ensure the bridge was level and stable, ready for traffic flow upon completion of the assembly process. The first step in asphalt reconstruction is milling. A specialized milling machine, often likened to a giant cheese grater on wheels, is used. This machine grinds away the top layer of damaged asphalt, removing inconsistencies and creating a uniform surface. As the machine moves across the road, it breaks up the old asphalt into small chunks. The milled asphalt material is not discarded but instead transported to a recycling facility. Here, the chunks of asphalt are cleaned and processed for reuse in new asphalt mixes. Recycling helps to reduce waste and conserve natural resources, making asphalt reconstruction a sustainable practice. Once the old asphalt is removed, the underlying pavement is exposed. Depending on its condition, further preparation may be necessary. This could involve repairing sublayers, filling in deeper potholes, or addressing drainage issues to ensure the longevity of the new asphalt surface. Before applying new asphalt, any remaining cracks and small defects are filled and repaired. This is typically done using specialized materials that prevent water infiltration and ensure a smooth transition between old and new asphalt surfaces. Trowels and other tools are used to compact and level these repairs. To bond the new asphalt layer with the existing pavement, a tack coat is applied. This sticky substance is sprayed onto the clean surface using a leaf blower and squeegee. The tack coat acts like glue, enhancing the adhesion of the new asphalt layer and preventing separation over time. Before paving begins, the paving machine, paver, is set up and calibrated for the specific project requirements. This includes adjusting the screed, which is the component responsible for spreading and leveling the asphalt mix to the desired thickness and width. Hot asphalt mix, consisting of aggregates such as gravel and sand, and asphalt cement, a petroleum-based binder, is delivered to the job site in trucks. The asphalt mix is heated to a precise temperature to ensure workability and proper compaction during paving. The paver receives the hot asphalt mix from the delivery trucks and begins the paving process. The mix is fed into the paver's hopper, where it is evenly distributed across the width of the machine. As the paver moves forward, the asphalt mix passes under the screed. The screed levels and compacts the asphalt to the specified thickness, typically ranging from 1.5 to 3 inches, depending on project requirements. Modern pavers use automatic screed controls to maintain precise thickness and smoothness. During paving, quality control measures are implemented to ensure the asphalt mix meets specifications. This may include density testing using nuclear gauges or other methods to verify compaction levels and uniformity across the pavement surface. Asphalt joints are crucial points where new pavement meets existing surfaces or where sections of fresh asphalt connect. These joints are carefully formed and compacted to ensure structural integrity and prevent water infiltration. After the asphalt is laid and compacted, any necessary finishing touches are made to ensure a smooth, uniform surface. This may involve hand tools or additional passes of the roller to eliminate any imperfections. Following closely behind the paving machine is a roller truck. This heavy machinery is crucial for compacting the newly laid asphalt. The roller compresses the asphalt, squeezing out air pockets and ensuring a dense, smooth surface. Proper compaction is essential for the asphalt's durability and resistance to cracking. Once compacted, the asphalt is smoothed out to eliminate any imperfections or irregularities. This may involve additional rolling or leveling to achieve the desired surface texture and evenness. On January 12, 2019, the world's largest concrete 3D printed pedestrian bridge was completed in Wisdom Bay Industrial Park, Baoshan District, Shanghai. Designed by Professor Xu Weiguo's team from Tsinghua University, in collaboration with Shanghai Wisdom Bay Investment Management Company, the bridge spans 26.3 meters in length and 3.6 meters in width. Inspired by the ancient Anji Bridge in Jiaoshen, China, it features a single arch structure with a 14.4-meter distance between abutments. A 1:4 scale model was constructed to test assessed structural integrity, confirming the bridge could safely support pedestrian loads. The bridge was printed using a 3D printing concrete system developed by Professor Shu's team, incorporating advanced digital architectural design and innovative printing technologies. The construction, which took 450 hours, utilized 2 robotic arm 3D printing systems, highlighting a significant achievement in digital construction and material science. An asphalt paver is a complex machine essential for paving operations, and understanding its functions and the critical steps to successful commercial paving is vital. Before starting a paving operation, the paving crew must address key considerations and complete a pre-paving checklist, including setting the screed, center toe points, paving width, main screed crown, slope extensions, and end gates. The auger height should be 2 inches above the surface being paved, feed sensors set, the auger chamber filled, and the screed lowered in the starting position. Ensuring a clean surface is crucial. It should be swept or blown before applying the tack, an emulsion that bonds asphalt layers. As the emulsion breaks and the water evaporates, it turns from brown to black, indicating readiness for paving. When the asphalt truck arrives, the dump man directs it safely to keep the hopper 1/3 to 2/3 full. The mix is carried by the conveyor to the augers, which distribute it to the front of the screed. Maintaining a constant head of material in front of the screed is essential for achieving the correct thickness and angle of attack. A rolling pattern is established for proper compaction, with the large steel wheel roller followed by the pneumatic roller for final compaction. Successful commercial paving involves additional considerations. The design of a parking lot is crucial. Poor design can lead to maintenance issues and a shorter lifespan. The paver, which moves in straight lines, cannot reach every nook and cranny, requiring handwork for areas like bullnoses. The base installation is critical. A well-compacted subgrade ensures the proper performance of the asphalt, similar to how a cake needs a solid foundation for good frosting.
Modular design enables easy assembly and diverse configuration possibilities. Components are reusable, minimizing waste and environmental impact significantly. Versatility shines as it seamlessly transforms into flood defenses, providing resilient barriers. Simultaneously, it adapts to serve as humanitarian shelters, showcasing its ability to meet diverse needs in challenging environments with ease and efficiency. Design facilitates assembly with minimal skills and basic tools, fostering inclusivity and empowering communities with limited construction expertise. Remarkable weight reduction, 88% lighter than traditional brick, simplifies transportation and assembly logistics without compromising structural integrity or functionality. Adaptable design allows for the seamless integration of electrical installations, enhancing functionality and ensuring modern amenities in constructed structures. Rapid assembly process ensures swift construction, saving time and resources while maintaining structural integrity and reliability. Launching CPS pontoons involves deploying modular units into water, aligning them, and securing using RPC connectors for stability. Precisely position the RPC by inserting its alignment key first. Detach CPS pontoon by disengaging connectors for independent deployment or maintenance. Securely attach RPC to the CPS for a stable pontoon connection. Remove the alignment key from the RPC, ensuring its accurate placement, then carefully insert the RPC into the designated port of the CPS. Confirm proper alignment and connection to ensure stability and structural integrity before proceeding with the pontoon system's use or deployment. One of the defining features contributing to its transport convenience is the modularity of the pontoons. These units are engineered to be modular, allowing for easy disassembly into compact components. This design enables efficient packaging and loading onto trucks or standard shipping containers, optimizing space and minimizing transportation costs. The ability to break down the pontoons into manageable units streamlines the logistics of moving them to even remote or challenging terrains. Moreover, Kumbh compatibility with diverse transportation modes ensures its accessibility to a wide range of project locations. Whether by road, rail, or sea, these pontoons can be transported without hassle, offering unparalleled flexibility to construction projects regardless of their geographical location. Furthermore, the modular nature of Kumbh not only simplifies its transportation, but also expedites the setup process upon arrival at the project site. The components can be efficiently unloaded and transported to the assembly area, ready to be swiftly reconfigured into the desired construction setup. The transportation stage also emphasizes the system's adaptability to varying project scales. Whether a small-scale coastal development or a large-scale offshore construction endeavor, Kumbh transportability remains consistent. Upon arrival at the project site, the modular units are unpacked and prepared for assembly. The simplicity of Kumbh design allows for a swift setup, minimizing downtime and expediting the construction process. The key highlight of this stage lies in the unique coupling and locking system employed by Kumbh. This system allows for seamless interconnection of the modular pontoons without the need for complex tools or extensive expertise. The components feature specially designed connectors that effortlessly link together, forming a sturdy and reliable framework. The ease of handling these connectors streamlines the assembly process, enabling construction teams to efficiently create various configurations, from simple platforms to complex structures. Flexibility is another hallmark of the assembly stage. The modular nature of Kumbh allows for configurations to be adjusted or expanded easily as project requirements evolve. This adaptability ensures that the system can accommodate changes in design or functional needs without significant delays or disruptions. Moreover, the assembly phase emphasizes safety and stability. The robust coupling and locking mechanisms ensure that the assembled structures possess the necessary strength to support substantial loads, meeting stringent safety standards prevalent in marine construction. The assembly stage also serves as an opportunity for innovation and customization. Construction teams can experiment with different combinations and layouts, optimizing the use of Kumbh modules to achieve the most efficient and effective configuration for the project's objectives. Comprehensive tests are conducted to evaluate the durability and stability of the assembled Kumbh structures. These tests include load-bearing assessments, where the structures are subjected to varying loads to verify their capacity to withstand heavy weights, ensuring they meet or exceed specified weight thresholds. Engineers meticulously analyze the responses, ensuring that the structures remain stable and secure under different load conditions, guaranteeing their suitability for demanding marine operations. Furthermore, buoyancy tests are conducted to assess the pontoon's flotation capabilities. These tests confirm that the pontoons provide adequate buoyancy to support the intended loads while maintaining stability and ensuring safety during operations. Engineers meticulously analyze the pontoons' performance to ensure they meet specified buoyancy requirements. The testing phase also encompasses operational trials, simulating real-world conditions. This includes assessing the system's response to environmental factors such as waves, currents, and wind forces. By subjecting the assembled structures to these conditions, engineers validate their stability and performance, ensuring they can withstand the challenges posed by the marine environment. Additionally, functional tests are conducted to assess the operability of any integrated mechanisms or specialized features within the ComboFloat system. Position the dock near the water. Sliding 8 feet floats halfway beneath the initial section for stability. Add the next hexagon section atop floats, sliding it snugly against the first for alignment. Check and align the corners to ensure a seamless fit at each end of the 16 feet connection. Secure corners with 3/8*1 carriage bolts and K-lock nuts for a robust connection. Use a 9/16 ratchet to securely tighten the fastenings for stability. Repeat the fastening process on the opposite corner of the hexagon. Insert 3/8*3 carriage bolts, flat washers, split lock washers, and nuts into pre-drilled holes along joists. Align floats with hanging fastener assemblies for secure and accurate positioning as illustrated. Arrange floats according to the designated pattern for optimal stability and functionality of the dock. Use a ratchet to securely tighten all bolts on the floats for stability and structural integrity. Position pre-cut bumpers onto the top decking for added protection and cushioning along the edges. For every 8 feet length of bumper, use 912*3/4 Tech screws, spaced 1 foot apart, securing them into the decking as directed. With the assembly complete, your hexagon-shaped dock is primed for launch. For a smooth transition into the water, a recommended rail system is suggested. Utilize a rail system of your preference to effortlessly slide the dock into the water. This method not only ensures ease of launching but also maintains stability and precision during the process, offering a seamless experience as your dock takes its place on the water. Spanning a vast expanse of 100,000 square meters, the piers embodied a golden sheen, fashioned from shimmering yellow fabric, supported by 220,000 high-density polyethylene cubes. An undulating pathway materialized just above the water's surface, a 3-kilometer-long walkway extending across Lake Iseo. Visitors were invited to traverse this surreal creation, a sensory journey from Solzano to Monte Isola, enveloping the island of San Paulo within its embrace. The meticulous selection of Lake Iseo stemmed from an extensive exploration by Christo, Vladimir Yavachev, Wolfgang Vols, Josie Kraft, and project director Germano Celent. Its allure lay 100 kilometers east of Milan and 200 kilometers west of Venice, presenting an inspiring canvas for their artistic vision. The floating piers, 16 meters wide and gently rising to 35 centimeters, featured sloping sides inviting participants to immerse themselves in this transient masterpiece. The artistry didn't confine itself to the lake. 1.5 kilometers of pedestrian streets in Solzano and Peschiera Miraglio donned the same fabric, extending the experience beyond the water's edge. This ambitious endeavor marked Christo and Jean-Claude's return to large-scale projects since their iconic work, The Gates, back in 2005. True to their ethos, the project's funding relied entirely on the sale of Christo's original artworks. An artistry-driven endeavor, it spoke volumes about their commitment to art's transformative power. Italy held a special place in Christo and Jean-Claude's artistic journey. Their repertoire boasted earlier projects like the Wrapped Fountain and Wrapped Medieval Tower in Spoleto, 1968. Wrapped Monuments in Milan, 1970, and The Wall, Wrapped Roman Wall in Rome, 1973-74. Each endeavor left an indelible mark, shaping Italy's landscape into a gallery of evanescent marvels. However, as with all of their transient creations, the Floating Piers bid adieu after its ephemeral display, adhering to the duo's principle of transience. Post-exhibition, every component underwent removal and industrial recycling, leaving behind only memories and perhaps a deeper contemplation on the nature of impermanence in art and life. The legacy of the Floating Piers transcended its physical presence. It offered a brief yet profound interaction, an invitation to traverse a pathway that was simultaneously real and ethereal, tangible and transient. It showcased the union of art and environment, inviting visitors to witness and partake in a fleeting spectacle, etching an unforgettable chapter in the narrative of contemporary art. In tackling the task of mitigating aggressive waves reaching up to 7.5 feet, 2.3 meters, enduring winter ice layers of 3 feet 1 meter thickness, and accommodating daily tides surging as high as 23 feet, 6.9 meters, Marinetics Breakwater had to be a paragon of strength and adaptability. The genesis formidable structure took place in Finland, where Marinetics engineering and design teams crafted the blueprint, but theory needed validation. Hence, a prototype was rigorously tested in wave tank laboratories, first in Finland at VTT and then in Croatia, ensuring its resilience against the tempestuous forces of nature. The actualization of this ambitious project involved the manufacturing of colossal concrete pontoons in Croatia. These critical components, constituting the backbone of the breakwater, had to endure the arduous journey from the Mediterranean coast to the distant shores of Canada. Transporting such massive concrete structures across continents wasn't without its challenges. The logistical feat of shipping these pontoons to Canada required precision and coordination. They had to navigate international waters, overcome logistical hurdles, and withstand the perils of transoceanic transport to reach their destination intact. Upon arrival in Saguenay, the installation process confronted another obstacle, a deep and uneven seabed. Anchoring the breakwater pontoon in such conditions demanded innovative solutions. Despite this challenge, the breakwater was efficiently installed, a testament to the simplicity of its structure and the robustness of its joint connections. In December 2018, as preparations for the Grand Kumbh Mela in Allahabad were underway, the construction of pontoon bridges took center stage in the monumental logistical endeavor. The Kumbh Mela, a revered Hindu pilgrimage, attracts millions of devotees from across the globe to the confluence of the Ganges, Yamuna, and Saraswati rivers. Ensuring safe passage and access for this colossal influx of people demanded planning and execution, especially regarding transportation infrastructure. Pontoon bridges, characterized by their floating decks supported by barges or boats, emerged as pivotal components of the Kumbh Mela's logistical framework. These bridges were strategically positioned to facilitate movement across the rivers, connecting different parts of the sprawling Mela grounds and the city of Allahabad. The process of constructing pontoon bridges for such a massive event involved a convergence of engineering prowess, logistical expertise, and stringent safety considerations. It commenced with planning, surveying the riverbeds, and determining optimal locations for the bridges based on anticipated foot traffic and logistical needs. The construction phase was a synchronized symphony of various teams and departments. Skilled engineers worked on designing the bridge structures to ensure stability, load-bearing capacity, and resilience against the natural forces of the rivers. The materials used, ranging from steel to sturdy wooden planks, were carefully selected for durability and buoyancy. Simultaneously, teams focused on assembling the pontoon units, carefully positioning them to form the foundation of the bridges. These units, comprising interconnected pontoons or barges, were meticulously anchored and secured to withstand the river currents while providing a stable base for the bridge deck. The assembly of the bridge deck was a process involving the laying and fastening of the platform over the pontoon structure. Skilled workers meticulously aligned and connected the prefabricated sections, ensuring a smooth and secure surface for pedestrian and vehicular movement. Safety protocols were paramount throughout the construction phase. Teams implemented rigorous inspections, quality control measures, and stress tests to ensure the structural integrity of the pontoon bridges. Additionally, measures were put in place to manage crowd flow, prevent overcrowding, and ensure the safety of the pilgrims using these bridges during the Kumbh Mela. The completion of these pontoon bridges represented a significant milestone in the ongoing preparations for the Kumbh Mela. These vital arteries facilitated the movement of millions of pilgrims, providing them with safe and efficient passage across the rivers, enabling them to participate in the sacred rituals and festivities of this revered event. On day 1, zero-footprint foundations were laid, employing environmentally friendly techniques that minimize soil disruption and promote sustainable construction practices. Day 2 focused on the assembly of modular steel frame flooring, ensuring swift construction while maintaining structural robustness and stability. On day 3, the flooring material was carefully installed, chosen for its durability and suitability to the building's function, enhancing both aesthetics and functionality of the space. On day 4, skilled craftsmen began by positioning and securing the first U-panels into place, aligning them to create a seamless foundation for the walls. These panels, engineered for both strength and insulation, form the structural backbone of the building. Days 5 and 6 saw the systematic installation of successive layers of U-panels, carefully interlocking them to create a robust and cohesive barrier against the elements. Each panel was precisely measured and aligned, with attention to detail paramount to ensure structural integrity and aesthetic appeal. By day 7, the walls began to take shape, with the distinct features of the U-panel system becoming increasingly evident. The efficiency of this construction method became apparent as the building rapidly transformed from a skeletal frame to a fully enclosed structure. Throughout this process, stringent quality control measures were enforced to guarantee the highest standards of craftsmanship and durability. Any discrepancies or imperfections were swiftly addressed to maintain the integrity of the build. On day 9, the focus shifted to the installation of the roof frame, a critical step in completing the structure. Carefully positioned and secured the framework, ensuring precise alignment and structural integrity before proceeding to the next phase. On day 10, roof panels were swiftly installed atop the frame, sealing the structure and providing protection against the elements. Safety equipment. Consult all tools and supplies. Check the condition of the base and prepare the plaster. Open some boxes and mix the pieces for a better distribution of color and fit. Use AC3 mortar for natural rocks in the assembly. Use a color close to the product. Prepare the indicated AC3 mortar following the brand's instructions. Moisten the base and the product before application. Apply the mortar to the wall with the toothed side of the 50 mm trowel. Apply the pieces, press and level with fingers or a rubber mallet. For cutting and finishing, use scissors and a saw machine. Repeat the process. Wait 12 to 24 hours to start grouting. Use acrylic grout for natural rocks for grouting. For best results, use a color close to the chosen pebble. For best results, use a color close to the chosen pebble. Moisten the product before applying the grout. Apply the grout and fill all joints well. Start cleaning with a sponge to remove excess grout. Use a wet brush to further remove grout and delineate large pebbles. Finish cleaning with foam. Wait for the curing time of the grout indicated by the manufacturer. The process began with pre-assembled balconies delivered from Sapphire's factory in Reading. Unlike conventional crane installations, where balconies are lifted directly from the lorry bed, this project required a more intricate approach due to limited access. Balconies were unloaded to the ground and equipped with lifting hooks, allowing for smooth integration with the crane's counterbalance offsets. With the crane hooks securely attached, the balconies were lifted into place one beneath the other, eliminating the need for ground-up installation and offering greater flexibility. The meticulous coordination between the crane operator, Sapphire specialists, and on-site team ensured each balcony was maneuvered with precision across the site. As the telehandler fetched the next balcony, the crane carefully transported the installed balcony to its final location. Sapphire's innovative counterbalance system maintained stability throughout the process, enabling seamless guidance by the on-site team. Constant communication and expert maneuvering ensured each balcony was smoothly positioned and secured to the building. Internal installers, equipped with guidance rods, skillfully directed the balconies into place, ensuring alignment with the building's facade. Once squared and securely positioned, balconies were fixed with specialist mechanical fastenings, guaranteeing stability and durability. The efficiency and expertise demonstrated by Sapphire resulted in a record-breaking achievement, with 22 balconies installed in just 6 hours. This feat not only exemplifies Sapphire's commitment to excellence, but also underscores their role as leaders in balcony innovation. Firstly, the rufous helpers serve as versatile brackets that can be clamped onto the seam of the roof. These brackets not only provide a sturdy platform for staging, but also double as steps, facilitating movement from one point to another on the steep roof safely. Next, the S5 PV Kit 2.0 comes into play. This kit allows installers to attach clamps securely onto the seams of the roof, providing a reliable anchor point for the solar panels. By utilizing the synergy between Metal Plus brackets and the S5 PV Kit 2.0, the need for costly rail systems is eliminated, resulting in significant cost savings. The installation process begins with the installers starting from the top of the roof and working their way down. This method ensures safety and ease during the installation process. Metal plus brackets offer flexibility, allowing for the installation of either double columns or single columns of solar panels. Throughout the installation, safety remains a top priority. Installers are properly tied off to metal plus universal safety anchors to prevent accidents. Additionally, the use of roofers' helpers as steps ensures that installers can navigate the steep roof with ease and stability. One of the key advantages of this system is its simplicity. The ultimate brackets can be easily engaged or disengaged, allowing for quick adjustments as needed. This simplicity translates to efficiency, saving both time and labor during the installation process. Furthermore, Mario mentions a forthcoming video that will showcase a complete installation of solar panels on an entire barn using this rail-less system. This serves as a testament to the effectiveness and reliability of the approach. The combination of metal plus brackets and the S5 PV Kit 2.0 offers a practical and cost-effective solution for installing solar panels on steep standing seam metal roofs without the need for rail systems. With safety, efficiency, and simplicity at the forefront, this method ensures a successful installation process and long-term viability of solar energy systems. Thoroughly clean the aperture, removing old silicone, debris, and ensuring a pristine surface. This enhances the installation's stability and longevity. Inspect and clean the aperture, removing any remnants of old silicone or debris. A clean and well-prepared aperture sets the foundation for a successful door installation. Using a spirit level and string line, evaluate the threshold's level. Ensure it aligns with the desired standards for a smooth installation. Adding packers as needed, gauge the level at various points to prevent potential issues later. A perfectly level threshold not only contributes to the aesthetic appeal, but also plays a critical role in the proper functioning of the door, safeguarding against misalignment and ensuring the long-term durability of the installation. Depending on the door style, consider whether to fit the bifold door with sashes in place or remove them for larger doors. The choice may impact the installation method. For this demonstration, the bifold door is fitted with the sashes in place, showcasing versatility based on specific project requirements. Adjust fitting strategies accordingly, following the manufacturer's recommendations for optimal results. Lift the door into position within the prepared aperture, using temporary packers to hold it in place. Loosely pack out the jambs and continuously check their level to prevent any twists or distortions. Ensure the door aligns parallel and plumb. Secure outer jambs at appropriate intervals with fixings, maintaining specified distances. The careful alignment during this step lays the foundation for a correctly functioning bifold door system, essential for long-term performance and durability. Position fixings strategically adhering to guidelines for optimal stability. Place fixings at a minimum distance of 150 mm from corners, ensuring they are no closer. Maintain a maximum center-to-center distance of 600 mm. Install a minimum of 3 fixings per side. This approach secures the outer jambs effectively, reinforcing the structural integrity of the bifold door installation. Secure the threshold using appropriate fixings through pre-punched drainage holes. Apply silicone around the drilled holes before inserting screws to prevent water ingress. Confirm the level of the threshold once complete. This fixation ensures a stable foundation for the bifold door, enhancing its durability and weather resistance. Using a timber lat to ensure parallel installation, fix the head into place, completing the outer frame. The head, aligned with the sill, contributes to the structural integrity. Verify its parallel placement for a cohesive installation. This fixation ensures that the bifold door functions seamlessly, with equal consideration given to both the top and bottom components of the frame. Fine-tune door gaps by adjusting the rolling mechanisms with an Allen key. Ensure smooth operation and equal gaps between doors. This step ensures a precise fit and functionality. Before glazing, remove beads from the first hinged sash. Install linear glazing platforms, lift the glass onto them, and use packers if needed. Toe and heel all sashes to maintain equal gaps. Silicone between glazing platforms ensures stability during the glazing process. Place linear glazing platforms for even support. Lift the glass onto these platforms from the inside, adding packers as required. This step lays the foundation for precise and secure glazing. After placing linear glazing platforms, lift the glass onto them, adding packers as needed. Toe and heel all sashes for equal gaps on the head and threshold. Silicone between each Atika platform ensures stability. Begin fitting the beading, starting with the shortest pieces, ensuring a secure and weather-tight glazing. Start by removing all beads from the first hinged sash, taking note of their original positions. Illuminate's unique design includes PVC beads that easily rotate out, or for powder-coated doors, conventional aluminum beads and wedge gaskets. For PVC beads, the longest ones can be arched and tapped into place with a plastic mallet, starting from the corners and working towards the middle. Ensure the beads are correctly placed to maintain the door's weather-tight seal and aesthetic appeal. Be in this process as the accuracy of bead placement directly influences the door's performance. The snug fit provided by the beads enhances both security and insulation. For powder-coated doors with aluminum beads, ensure they align precisely with the glass. This step involves attention to detail and careful placement to guarantee a seamless finish. Gently tap the beads into place with a plastic mallet, ensuring equal pressure across the length. Taking a systematic approach, work on each sash individually. As you replace the beading, repeat the toe and heel process for all sashes, maintaining equal and parallel gaps. Systematically repeat the toe and heel process for each sash individually. This ensures consistent and parallel gaps on both the head and threshold, maintaining the structural integrity and smooth operation of the bifold door system. Thoroughly assess the finished doors for smooth functionality. Verify that the rolling mechanism operates seamlessly, ensuring equal gaps between each door and weather-tight seals. Make any final adjustments as needed. Fine-tune vertical door alignment by using 1 mm packers at each hinged point. Adjust by removing or adding these packers, providing up to plus or minus 1 mm adjustment. Ensure equal spacing on the hinge, and use a maximum of 3 packers per hinge. For chute bolt adjustments, remove the 4 screws and the plastic cover. Twist the chute bolt if necessary, then replace the cover and screw back into place. A 90-degree twist results in a 1 mm increase or decrease in compression against the outer frame. Ensure the handle and locking mechanisms operate smoothly on each door. Confirm the bifold action is free-running and that locks engage correctly when closed. Verify the door magnets are fully engaged when open for continuous seamless operation. Verify that door magnets are fully engaged when doors are open. Proper engagement is crucial for the seamless operation of the bifold door. Thoroughly clean the door track with a soft brush to remove any debris. A clean track ensures the smooth operation of the rolling mechanism, preventing potential disruptions in functionality. The installation process begins with an assessment of the roofing structure. Oi's experienced technicians evaluate the suitability of the existing roof for the integration of solar elements. This initial step ensures that the solar roof is seamlessly incorporated without compromising the structural integrity of the building. Before commencing the installation, the team at Oi ensures that all safety measures are in place. Safety is a top priority during the installation process, and the team adheres to industry standard protocols to guarantee a secure working environment. Once safety measures are established, the actual installation of roofit solar begins. The roofing material, equipped with integrated solar panels, is expertly positioned over the existing roof structure. Oi's technicians secure each solar panel, ensuring a tight and durable fit that can withstand various weather conditions. The interconnection of solar panels and electrical components is a crucial aspect of the installation process. Oi's skilled technicians carefully connect the solar roofing system to the building's electrical grid, enabling the seamless transfer of solar-generated energy to power the structure. Quality control is inherent in every step of the installation. Oi conducts thorough checks to verify the proper functioning of each solar panel, ensuring optimal energy production. This attention to detail guarantees that the solar roof operates efficiently, maximizing its potential in harnessing solar energy. As a final step, Oi provides comprehensive guidance on the operation and maintenance of the installed solar roof. This includes educating clients on monitoring energy production, understanding system performance indicators, and offering insights into routine maintenance practices.